on. We're going to talk about wave interference now. So I guess the first question is, what do we mean when we say interference of waves? Well, basically, waves interfere when they overlap within the same medium. So interference is what we would call a superposition or adding up or overlap of two or more waves moving through the same medium. When waves overlap, when they interfere, the resulting amplitudes of those waves, the overlap, the amplitude of the oscillation in the medium is basically just the algebraic sum of the two individual waves. That probably sounds kind of complicated, but hopefully the visuals that we're going to look at help a little bit with that. So if you have two waves interfering, so here's what we're going to think about. Let's say I have two wave pulses that are moving in the same medium towards one another. When those two waves are at exactly the same position, when they overlap in that medium, then the resulting pulse amplitude, the resulting perturbation in the medium is going to be the algebraic sum or the overlap of those two individual wave pulses. So when this blue wave and this red wave come to the point where they overlap, you're going to see one big wave where they are, basically both moving the medium to some degree at the same position at the same time. Now, these two waves are going to continue moving past one another. And so you're going to have that overlap, that moment where their amplitudes add together, and then they're going to continue moving in the opposite direction. If we have these two waves, so this one is a trough, so it's below the axis. These two waves are going to move towards one another, and at the moment where they overlap, you're going to see a single wave pulse that is basically the algebraic sum of these two individual amplitudes. They're going to overlap for just a minute, and then they're going to move past one another. This is what we call constructive interference, when two waves overlap in such a way that the resulting amplitude is greater than the individual amplitudes of the separate wave pulses. Now we have another condition that could happen. I have this upward wave pulse and this downward wave pulse, and when they overlap, we're going to do an algebraic sum of their amplitudes. So I've got this positive amplitude and this negative amplitude, and so there's going to be an instant in which these overlap, and you'll see no wave there at all. Now, this wave pulse is moving moving to the left, and this wave pulse is moving to the right. And so after they have that moment where they overlap, this wave pulse, the one that is the blue one, is going to eventually be over here. It's still going to be a negative amplitude, and this other wave pulse, the red one, is going to have moved forward, over here. So it's moving this way, the blue one is moving that way. But at that moment where they overlap, the two perturbations in the same medium are going to basically push the medium in opposite directions, and they're essentially going to cancel each other out at that point. So we call that destructive interference if the two waves overlap in such a way that the resulting or combined amplitude is less than either individual wave. Constructive interference happens when the two waves overlap in such a way that the resulting amplitude is greater than either the individual waves. So for example, if I have two wave pulses that are in the positive direction and they overlap, you're going to get a bigger amplitude overall when they are interfering with one another. What if the amplitudes of the waves have different amplitudes and directions? So what if I've got this small red wave and this big blue wave? What are they going to look like when they overlap right in the middle? Well, at that point where they both overlap, you're going to have partial destructive interference. But it's still going to be destructive interference because this red wave here is pulling the medium upward, and the blue wave is pulling the medium downward just a lot more. And so overall, at this point where they overlap, you're going to have a wave that is partially downward because this big downward pull by the blue wave is being canceled out partially by the upward pull on the medium by that red wave. So when they overlap, you're going to have, you know, a partial canceling, partial destructive interference. But what happens once the waves pass one another? Well, after the waves have passed one another, they're going to look exactly the same as they did before. After the waves have passed, you're going to have this blue wave continuing to move in this direction. So this is our before picture and this is our after picture. The red wave continues moving this way. They haven't really affected each other at all. These are both just disturbances that happen in this medium. So maybe I've got rope or a string or a, you know, water surface. And the particles themselves might be oscillating, but they're not moving their locations. And so I have an upward oscillation and a downward oscillation. Those oscillations are just energy moving through the system, but they're not taking particles with them. So there's no change left behind, and there's no way that this oscillation is going to affect this oscillation separately. They both, however, have an effect on the medium. In this case, they pull the medium in opposite directions and kind of cancel out each other's pulls. We could just like do straight up addition here, you know? I have pictures drawn on the previous slides, but basically we can think about it like this. If I have a wave pulse that's an amplitude of say +1, and I add that to a wave pulse of amplitude +1, overall the amplitude that I'm going to get should be like +2. If I have a -1 amplitude and a -1 amplitude and they overlap, it should be like a -2 downward, I guess, trough when I combine those. If I have a +1 wave pulse and a -1 wave pulse, when I add these together, I'm going to get, you know, basically no wave at all. And if I have a +1 amplitude and a -2 amplitude, I'm going to get partial destructive interference. So it should look like a -1 sort of wave pulse. You will get a chance to test this out with some simulations, and also there'll be some quest problems where you're looking at overlaps of waves too. I don't think I'm going to do too many more examples here. But I like this one. So the pulse on the left is moving to the right, and the pulse on the right is moving to the left. What do you see when the two pulses overlap? So I could have you just like draw it out. You might want to try drawing it out now. If you want, you can pause the video and then try to draw it out. I'm going to scroll to the next page, which is going to have some answer options for you. Yeah, unfortunately I scrolled all the way to the end. Give me just a second. All right, so here's your answer options. So we're looking for waves when these are overlapped and centered on one another. So one way to look at it is to try to break these down into separate pulses. So this looks like a pulse amplitude of -1, okay? But it's also a wider wave. So this has a width of 3, notice. So I'm going to want to make sure that whatever wave I had here has that width of 3 in it. And this has a height of 1, 2, 3. This is a height of 3 for that amplitude. But what you might want to notice is that when I take this height of 3 and I overlap it with -1, I should find that that amplitude, when these are directly over one another, this drops our medium down by 1 and this raises our medium up by 3. And so overall, my total height should only be -1 plus 3. So it should have 2 for the amplitude, right out the middle. That means this one's out. This one I think is out. This one looks right. So I've got 1, 2, 3 for my amplitude there. And I have an overall width here of 3. And this on the side, when I think about taking this and transposing it and moving it over here. And that's what our wave should look like. So I think it's B. You'll get more opportunities to do this on the Quest as well, and in our simulation game. All right. I'm going to introduce some vocabulary. I have a lab that we'll use to look at this in a little bit more detail. But we have a specific word that we use to describe the overlap or the interference of waves that are really, really close in frequency. The term we use for that is beats. So that describes the characteristic of like a loud and soft pattern that you get when you have two really close frequencies, but they're not exactly the same frequency. So this would be the sound that you would hear when you are, say, playing a tune, two sounds that are really close but not exactly the same. So if you've ever been in like a musical group, whether singing or band or strings, when you have two instruments that are trying to play the same notes, but it's not quite right. It's just a little bit off. And that sound of two things being out of tune with one another tends to make sort of an oscillation in the sound that you're hearing, the combined sound. It sort of sounds, I'll have to get out a speaker so that I have some sound demonstrations that I'm going to record later, so you're going to listen for this later. But it sounds kind of like a wah, 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 when you're playing a sound and you have another one that's out of pitch. And what's happening is you're getting constructive interference and destructive interference kind of alternating because they're really, really close in sound. So you get basically a knocking out of that sound in a very, very high frequency oscillating pattern. Basically, it's what musicians would describe as two sounds, two instruments, or two singers, or two sources of sound that are out of tune with one another. And it is all because of destructive interference, the fact that sound is a wave. So this is, I think, good evidence of wave-like behavior in sound. We can see destructive interference and constructive interference with light. We can see it with sound, and we can see it with water waves. I'm going to put this up here, but it's not super important. I'm not going to expect you to know this equation. I'm not going to give you any Quest problems on it. But the frequency of the beats, like how quick that oscillation is of that drop out of the sound when you have two things that are out of tune, the beat frequency has to do with how close the two frequencies are to one another. So if you hear a really long frequency beat, so a sound like wah, 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 okay, so that's really, really long time between the high and low parts of that sound, then that means that the two pitches you're playing are actually pretty far from one another. Or sorry, let's see, when that frequency is small, then they're really close. And as that frequency gets bigger, then you're going to have an increase in that oscillation. So it may go wah, 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 something like that. And it'll get further away from being the same frequency. And eventually it'll sound like two different notes are being played. That beat frequency being a low number means that you are almost in tune. So you can use that sound to kind of try to find, or put two sounds in tune with one another. And again, I'll do a demonstration of that pretty soon. And we're at the end. So that is pretty much all I needed to talk to you guys about in terms of interference of sounds. So we'll be back with standing waves as our next topic.